Dear students, welcome back to the next lecture of digital communication. So in the last class, we were discussing about the optimum receiver for binary communication, and we derived that the optimum receiver in the presence of additive white Gaussian noise is nothing but a minimum distance receiver that minimizes the probability of error. So basically, if your received signal is closer to your signal 1, then you decide that signal 1 was the actual signal that was transmitted, and if your received signal is closer to signal 2, then you decide that the signal 2 was the actual signal that was transmitted, and in that way you can minimize the probability of error. And we derived, uh, starting from the expression of probability of error, we derived that if your two signals are equally likely, then all you need is a decision rule, that is this one, which gives you the optimum receiver. So we will move forward with these concepts at the back of our mind. So let's say that how you will implement such a receiver. Like this is the mathematical expression of the optimum decision rule, which says that if your received signal is closer to one of the signal, then you are you are making a decision on the favor of that particular signal. But in terms of actual receiver circuit design or a receiver hardware design, what does this imply? So we will see that today. So so the first concept is the correlation receiver, and let's see how that can be implemented from the concepts that we derived so far. So let's say this is a correlation receiver. So you have your received signal RT, which is the signal transmitted SIT plus the noise WT. Okay, so SIT will be S1T or S2T depending on whether a 0 is transmitted or a 1 is transmitted. So now you are correlating the received signal with the phi 1t and phi 2t separately. Okay, so basically these are your orthonormal basis functions. So if you correlate RT with phi 1t and then integrate between 0 to TB, then basically what you get here on the upper arm is the integral of between 0 to TB of your RT times phi 1t dt, and this is nothing but your R1. Okay, so this is the first component of your received signal. So your received signal RT can be presented as this, right? So R1 is the phi 1 component of your received signal, and R2 is the phi 2 component of your received signal. Or in other words, if you have a two-dimensional space like this defined by phi 1 and phi 2, your received signal is here, which is R is a vector, and it has two components, R1 and R2, right? So so you can obtain R1 by correlating your received signal with phi 1t and then integrating between 0 to TB. Actually, the whole operation is called correlation. So you multiply with phi 1 and then integrate, and then you get R1. Okay, so here you are getting R1 in the first arm, and the next below arm you are getting R2 by doing the same operation with phi 2. Okay, and notice that you are sampling at t equal to TB. So So basically these are continuous signals, all these are continuous signals, and if you multiply, integrate and sample at each TB seconds, then you will get these uh, these samples of R1 and R2, and you are basically observing these samples of R1 and R2 over time. Okay, so as your time progresses, so at let's say t equal to TB, you are observing R1 TB. At t equal to twice TB, you are observing R1 twice TB, and all this is happening in the first arm here, and in the second arm the same thing is happening. So at t equal to TB, you are observing R2 TB. At t equal to twice TB, you are observing R2 twice TB. So all these samples of the different components of the received signal are observed, and you are having a circuit here. Imagine this is a box which has some circuitry inside that is computing these terms. Okay, so basically you are computing the distance. So R1 minus SI1 square plus R2 minus SI2 square. So you know SI1 and SI2 because you are transmitting the signal, and in the receiver you are obtaining R1 and R2, so you can now compute this term. Okay, and you are choosing the smallest of this number. Okay, whichever is smallest out of these terms, because this is essentially the distance actually, so you are having a minimum distance receiver, so whichever is minimum, you are making a decision in favor of that. So if your R1 minus SI1 square plus R2 minus SI2 square is smaller for I equal to 1, then you decide that the S1 was transmitted, that was, let's say, corresponding to 0, and if your R1 minus SI1 square plus R2 minus SI2 square is smallest for I equal to 2, then you are deciding that S2 was transmitted. So actually you are computing this whole term, so this minus this. Okay, this is N0 log of Pi. Okay, so the whole thing is computed, and whichever is smallest, you are taking a decision in favor of that. Okay, so this is what is happening. Okay, so this is basically you are computing these terms in your this box circuit. Okay, and the left hand side is for S1 and the right hand side is for S2, the corresponding terms for S2, and then you are deciding which one is smaller. Okay, so if S1 is smaller, the corresponding term for S1 is smaller, which is denoted by this sign, then you are deciding 0 because S1 is corresponding to 0. And if your S2 is smaller, if this side is smaller, which is denoted by this term, then you are deciding 1 or S2 because S2 is corresponding to 1. So now if you just simplify these equations a little bit, then you come up with this linear equations. Okay, so you can see that the square terms are cancelling on both sides. Okay, R1 square and R2 square, these terms are cancelling. Okay, so and S11 square, S12 square, this together gives the energy of the signal S1. So S11 square plus S12 square is actually E1. Okay, plus E1. Okay, and S S21 square plus S22 square is plus E2. Okay, and R1 square is cancelling, R2 square is cancelling because they are the same on both sides, and these two terms remain as it is, and then we are left with these cross terms. So if you now arrange them together, you will see that you get a linear equation in R1 and R2. Okay, so so if you further simplify, bring them all on one side and collect the coefficients. So basically if you do S21, okay, and if you bring this R1 S11 this side, so you will get S21 minus S11 times R1 plus, so you have S22 here, so S22, if you bring this term this side, then this will be minus S12 times R2. Okay, and then let's keep everything else on this side. Okay, so 1, so this E2 will be this side, so E2 minus E1 by 2, and then you will have N0 by 2 log P1 by P2. So these right hand side terms are all known before, so you know, since you are sending the signals from the transmitter, you know what their energies are and what the probabilities of those signals, etc. And this N0 is also a constant. So the right hand side of this equation is a constant. Okay, if you look from the receiver side, so in the receiver you see that there you have a linear equation in R1 and R2. So some constant times R1, again the signal coefficient, these are the signal coefficients, these are also known, so these are also constant with respect to the receiver. So some constants time R1 plus some constant time R2, if that is greater than some other constant, then you decide 1. If it is less than some other constant, then you decide 0. So basically this is the equation of a straight line. If you look into the coordinate plane, that is the signal space, and you have a straight line in R1 and R2. Okay, so this straight line will be somewhere here. Okay, and this straight line actually gives you a decision boundary. Okay, so this straight line is called, whatever I wrote here, this equation can be plotted as a straight line in this phi1 phi2 plane, and this straight line is called the decision boundary. Okay, and let's say this term, this means that if it is below this, then you decide signal 1 was transmitted. If it is above this, then you decide signal 2 was transmitted. So all the points above this straight line is for signal 2, all the points below this is for signal 1. Or in other words, you have divided the entire signal space into two regions. You remember we started with this concept of R1 and R2 when we were deriving the expression for probability of error. So essentially you end up in the same thing. So you are dividing the signal space into two regions. Since we have two signals, we are talking about binary communication, and one of these regions belong to one of those signals. So if my received signal falls in this R1 region, then you decide for signal S1. If your received signal falls here, then you decide for S2. And this is the boundary, and the equation of the boundary, this is a straight line. The equation of that straight line is given by this, whatever is given here. So and also let's say if I remove everything, let's say, so this basically also Uh, if you look into these terms, this also gives you that this is the dot product of the vector r, that is the received signal, with Si. So this is the dot product of vector r with S2, and this is the dot product with S1. Okay, so you can look at the correlation receiver in that form as well. So you can do all those things which were same in the previous implementation of the correlation receiver, but whatever comes after is different here. So you form the dot product here. Earlier you were computing the distances, but now you form the dot product, then add these bias terms here. Okay, and then you choose the largest of this. Whichever is largest, you take a decision in favor of that. So this is what is happening. Okay, uh, by this equation. So this is another implementation of the correlation receiver. Now both of the implementations that you saw so far were like, multiplication and integration. Those are fine from the mathematical analysis point of view. Okay, if you are analyzing the receiver mathematically, then these are fine. But in reality, it's very difficult to, let's say, design an integrator like this. Okay, I'm not saying it is impossible. Integrators can be implemented with circuits, but this is very difficult. So the idea is that if you can replace the whole thing, this total operation of multiplication and integration, by a filter whose impulse response is defined as this. So H1T is the filter whose impulse response is phi 1 TB minus T, and H2T is phi 2 TB minus T. Then you can show that whatever R1 and R2 you are obtaining by filtering RT through these filters and then sampling every TB seconds, they are equivalent to the operation of this. Okay, this and integration. So so these filters are called matched filters. So this filter H1 in the upper arm is matched to phi 1, and in the lower arm this filter is matched to phi 2. Now let's see how these are equivalent. Okay, so let me go to the whiteboard here, and so let's say I have, let's say, what is the expression of R1 and R2? Okay, R1 and R2, the two components of the received signal which you are obtaining here. Okay, this R1 and this R2. This is basically integration between 0 to TB. This one is the received signal multiplied with phi 1. This is R1, and similarly this is R2, right? This is from the definition. Okay, so now let's draw a line and let's see this side what is the output of the matched filter. So let's say, if you look again, here the matched filter output is basically the convolution of this RT with H1T. Okay, and then R1 is that whatever is that convolution sampled every TB seconds. So let's first look into the convolution. So let's say your your R1 is basically let's say this is the integral or no, sorry. Um, let us define the output of this stage before the sampling as y1t and y2t. Okay, so basically um, let's say your R1 is basically y1 t sampled at every t equal to tb second. Okay, and R2 is y2t sampled at every tb seconds. And what is my y1 and y2? Y1 and y2 are basically the convolution of RT with this matched filter. Okay, so let's define that here. So where your y1t is the convolution of RT with h1t. Okay, and y2 is the convolution of RT with h2t. Now let's look for this example. So what is RT? Like this convolution can be written as right this form. Okay, so let's look into this. So this will be, so your h1t is phi 1 tb minus t, right? So I will use this expression here. So this will be let's remove this part for the time being to avoid confusion. So R tau, and then h1t is this, so I can write h1t minus tau as phi 1 t minus tb plus tau d tau. Okay, so so that's what my convolution expression is. Basically in this integral, this tau is actually my my variable. Okay, so I'm operating on tau, so I will put tau, I will replace tau with this thing. Okay, so this will give me, now imagine that so R1, let's say, is basically y1 t at t equal to tb, right? And y1t is this. Okay, so if I put t equal to tb in this expression, this expression will turn out to be this expression. If I put t equal to tb, then this 2 will cancel and only I'll be left with tau. So I will have this, and this is indeed R1, right? We started from here. Okay, so this is R1. This is the integration of R tau with phi 1 tau. Okay, so you can see that you can show the similarly that R2 is also R tau phi 2 tau d tau using the same logic. Okay, so both sides are equivalent. This is the matched filter output. Sorry, this is the matched filter output. This is the matched filter output, and this is the correlation receiver output. Okay, so both sides are equivalent. So you can define the matched filter like these, and then you can have a filter that does the same performance. You can have R1 and R2, and you can obtain the same result. And then you have the decision circuit as usual, where you are comparing the distances uh, and then take the decision on the favor of the minimum distance. So let's do an example. So consider that we have a signal set S1, S2, which can be represented by orthonormal function phi1, phi2 as follows. So let's say S1t is phi1t plus half of phi2t, and S2t is minus phi1t plus phi2t. So if your phi1t looks like this and your phi2t looks like this, then your S1t and S2t will look like this based on these expressions. Okay. So now you can represent S1 and S2 on the phi1, phi2 plane like this. So here is your S1 and here is your S2. Okay, and then these are the expressions. Okay, the phi1 component of S1 is 1 and the phi2 component of S1 is half. Similarly for S2t, the phi1 component is minus 1, and for phi2t component this is 1. Okay, so now projecting the received signal RT on phi1t and phi2t and applying the decision rule. So now let's imagine that my received signal is somewhere here. I don't know where it is. Let's say after noise addition, my received signal is somewhere here. Okay, let's say this is my RT. Okay, so all I need to now do is to compare the distances between RT and S1t and RT and S2t, and whichever is smaller, we will make our decision in favor of that particular signal. So let's say if I calculate the distance of the received signal. So received signal has these components R1 and R2. So the usual distance, Euclidean distance formula is applied. So this is the left hand side is the distance from the received signal to S1. So we have R1 minus S11 plus R2 minus S12, both squared. And then this side we have R1 minus S21. S21 was minus 1, so this is R1 plus 1 square plus R2 minus S22 square, and then this term log P1 by P2. Okay, so we are assuming N0 here to be 2. Okay, so this N0 by 2 term is 1 here. So now if you simplify this, you will get this equation of a straight line. Okay, so as I was explaining a few slides back, so therefore the decision boundary is given by this straight line. Okay, so if you draw a straight line, this equal to 0, then you will get the decision boundary like this. So this is, here is your S1, here is your S2, and then this is your decision boundary, which is given by this particular equation. Okay, so so after you simplify this minimum distance rule, you get this equation. Okay, and whatever you get on this side, if you bring all the terms on one side and keeping the other side 0, then this equal to 0, this set equal to 0 is the equation of a straight line, that is the equation of your decision boundary. And this decision boundary is drawn here. So you can see this decision boundary is nothing but the perpendicular bisector of the line joining the two signals. Okay, so whatever falls in this area, okay, to the left, to the right of this decision boundary, that belongs to S1. So if your receive signal falls here, then you can straight away decide that S1 was transmitted because it falls within the region R1 that corresponds to S1, and this is your region R2, and this corresponds to the signal S2. So if your receive signal falls somewhere here, let's say, then you can straight away decide that S2 was transmitted. So this is how things get simplified if you represent your signals in the signal space, and that's why we were doing all this. We were studying signal space, we studied Gram-Schmidt orthogonalization, and then we found a means to make an optimum decision just by looking at the relative position of the received signal corresponding to the transmitted signal. Now this is the case where your P1 and P2 are same. Okay, if your P1 and P2 are not same, then there will be slight adjustments. So for example, if your P1 is small compared to P2, then this line will shift a little bit to the right. Okay, if your P1 is larger compared to P2, then this line will be shifting towards the left. So whichever signal has higher a priori probability, the line shifts towards line shifts away from that. So in this case, the a priori probability of S2 is smaller. Whichever signal has smaller a priori probability, the line shifts towards that. Okay. So this is something which is very interesting. Okay. So let's do another example. Let's consider the following two orthonormal functions and the signal sets. Okay, S2 and S1. So your phi1 is given, your phi2 is given. Okay, your phi2 basically looks like this, your phi1 is this. Okay, and your S1 and S2 are given in terms of phi1 and phi2 as usual, like this. Okay, so S1 is phi1 minus phi2, S2 is phi1 plus phi2. So you can see that both the signals have equal energy. If you do the math, then you will see E1, E2 both are 2. Both have common component phi1. Okay, so intuitively we would expect that only the component along phi2 will help us distinguish between the possible transmitted signals in the presence of noise. So we will have, let's say, if you draw the decision boundary, so both these signals S1 and S2, you see the phi1 component is the same. Okay, only the phi2 components are different, 1 and minus 1. Phi1 component is 1 for both the signals. So in this case, if you draw the decision boundary, then the decision boundary is this one. Okay, so basically it's only the phi2 component that is necessary to judge, the received signal with respect to the transmitted signal. Okay, so in such scenario you can only have one matched filter. Okay, so you just work with the phi2 component. So you have the received signal, multiply with phi2 and then integrate and sample, and you see R2 here, and you just figure out if your R2 is greater than a threshold or lower than a threshold. So if you go back to the figure again, if your this is the threshold, this decision boundary itself gives you the threshold. So if your R2 is greater than this threshold, then basically you are closer to S2. Okay, and in that case you can take a decision that S2 was transmitted. So if your R2 is greater than this threshold, you decide S2. If your R2 is less than the threshold, then you decide S1 for this example. Okay, so all you can do is just one correlation receiver, or in other words just one matched filter. Okay, because we also showed that these two are equivalent. So we can have only one matched filter, and then a simple comparator circuit where you are just checking if your R2 is greater than a threshold or lower than a threshold. So what does this imply? This implies that if you can manage to represent the signals in such a way that they look like this, okay, they look like this, 2 points which have a same phi 1 component, let's say, then you can just have one matched filter and a comparator to implement your receiver. So is there a way to, let's say, represent the signals in a signal space such a way that their phi 1 components are same, and then you can have a single matched filter implementation? And the answer to that is yes. So let's take this example. Let's say we have the initial scenario where we have phi 1 and phi 2, and your signals S1 is here and S2 is here. Okay, imagine this scenario. Okay, this figure has so many things, but let's focus on this one first. So phi 1, phi 2, and then here is your signals. For your understanding, I have just drawn it here in this way. Okay, so now if you can rotate the axis, okay, let's say I rotate the set of axes by an angle theta. Okay, so this is rotated like this in such a way that the new set of axes denoted by phi 1 hat and phi 2 hat, okay, is such that the signals in the new set, if you look, let's change the pen color. Okay, so if you see the new set with the blue color, you see only the axes are changing their position by angle theta. Signals are always the same, they are remaining same. But if you now look into S1t and S2t from the perspective of this new set of axes, then you see that you have the phi 1 hat component for both this signal is same, and the phi 2 hats are different. Okay, so if you define the new components as S11 hat and S21 hat, they are same, and S22 hat and S12 hat are different. Okay, so this is the same as the example that we did. Okay, so if we can do this, then we can have a single matched filter implementation of the receiver, and we can do this transformation, this angular rotation by theta, by this mathematical expression. So you have the original set of axes defined by phi 1t and phi 2t. If you do this transposition, then you will obtain phi 1 hat and phi 2 hat. So phi 1 hat is basically the new set of axes is given by this. So phi 1 hat t is nothing but cos theta phi 1t plus sin theta phi 2t, and phi 2 hat t is minus sin theta phi 1t plus cos theta phi 2t. So by this simple transformation, where theta is the angle of rotation, you can obtain two different orthonormal basis functions, phi 1t and phi 2t, which can represent the signals, same signals, but geometrically these are represented in a different set of axes defined by phi 1 hat and phi 2 hat, where the signals have a same phi 1 hat component and different phi 2 hat component, and in that way you can have a single matched filter representation where you only observe R2 hat and check whether it is greater than a threshold or lower than a threshold, and the threshold itself is given by this expression. Okay, so you can have a single matched filter matched to phi 2 hat, and then you can obtain R2 hat, and then you compare whether that R2 is greater than the T or lower than T, and you decide 1 or 0 based on that. So this is a trick that you can apply just to represent the receiver with a single matched filter, because a single matched filter can give you less hardware complexity and less costs. So if you remember the example 2 of the last lecture, so we had S1T and S2T, and they were represented as this. So in that case, your original S1T was here compared to phi 1T, and S2T was here, and then if you rotate the axis by an angle pi by 4, then this is the equation of the transformed orthonormal basis functions, okay, based on this formula here. So if you put theta equal to pi by 4, you can get these expressions here, and then and then you can see that you have the new set of axes, which is the new set of axes is such that you have the same S11 and S21 hat components and different phi 2 hat components. So here also you can have a single matched filter representation. So I'll stop here today, and we'll see you in the next lecture. Thank you.